Hey, it's Bloom and Glare. Today we're going to be covering how to create a large simulation with around 1,000,000 particles using the new Vellum solver. And it should be a pretty easy one, but I'll go ahead and show the end result. So okay, so there's a lot of geometry that's being used, but it's very similar to set this up. So let's just hop into Houdini. By default, I always save the file when I begin, just so there's a backup that's created, just in case things crash, which they inevitably will. I've made this before, so I'm just going to go ahead and overwrite it. And the first thing we'll make is the actual collider geometry. So we're going to drop a tube, dive into the node, and then convert it to a polygon. I want this to be, relatively high fidelity, so let's bring this to 64. The height, I'm just going to make it maybe 0.15. Okay, so nothing too deep. Some of the references that I'm using for this tutorial are just some high-end cosmetic photography. So these are some of the, I guess, this is some of the materiality that I'm using as a reference, especially these types of things, the granules, which is pretty easy to achieve with Vellum. So we'll be looking to make a container that's similar to that. And one of the things you have to make sure to check is end caps, okay? And by default, that's just gonna add, 2 caps to your geometry. Then we're gonna delete one of those, so just hit select the top, hit delete on the keyboard, and by default, when you do that, Houdini automatically creates a blast node for you, and that's just storing that deletion from the source geometry. Okay, so what we want to drop now is a node to add some thickness to this, and for that you can use a poly extrude. Okay, just enable that, and let's just try and give it some distance here in the extrusion. Nothing too crazy, maybe 0.1, 2, even 0.1 is fine. Okay, so you might be wondering, why you have this this purple or blue coloration inside here, and it's because this isn't actually closed geometry. You can see, if I zoom in, you can see the cap here, and this coloration is basically showing you that you're looking at an inverse normal. So this is the interior of the geometry, so we need to close that off, and there's a handy little dialog box here called output back that will close it for you. Okay, there you go, and you've got a beautiful ashtray. All right. We just want to round off those edges just so we get a little bit nicer play with the particles, and for that we'll use a poly bevel. Okay, and again, this is just really basic kind of modeling. I'm definitely more comfortable modeling in other 3D software suites, but this should do. So with the poly bevel node enabled, go to fixed distance and just give it, just a tiny bit, maybe 0.75. And by default, you can see we're getting these weird kind of pinches in the geometry. And to get rid of that, just disable allow vertex splits. You can add as many divisions as you want. I think even one is fine for this tutorial. And then there are a couple of options here for the fillet shape. So you can go solid, you can go crease, and you can see these a bit better. Chamfer. You'll be able to tell a little bit more what's going on if I increase the fixed distance. So round is going to give you a rounded shape, which I prefer. You can go chamfer, which will just kind of give you this nice angle here. And you get the same angle in here. Crease is a bit weird. Solid, a bit weird as well. Okay, so I would, if it were me, I would choose between these two. I'm going to go round. And we'll just enable the grid so I can see where I'm at here. Okay, and that's essentially it for the collider. So we'll drop a null. And let's just call this collider out. Enable. And oops. Call that collider. Okay, so this is what our grains are going to be colliding with. Now we need to make the source for the grains. And how do we do that? Well, it's very simple. We'll drop a circle. Okay, and by default, it defaults at the XY coordinate plane, and we're just going to change that to ZX or ZX. And let's raise this to 0.1. Okay, just so we can see what's going on here. Maybe 0.075. Just so this geometry comes a little bit over the top of our collider. Then we're going to drop the same nodes, so a poly extrude. We're going to output the back. And for distance, really low number, maybe 0.04, sorry. Okay, and you just want to make sure that that's not colliding with this geometry, otherwise your particles are going to be trapped inside here. So we can just go to okay, I think it looks okay. Yeah, we've got a lot of space, so maybe let's just extrude this a little bit more, maybe 0.06. Maybe even more actually, 0.1. Oops. Okay, so you can see there's still a fair amount of distance here, and this will drop down eventually anyway. I'm going to increase this one more time. Okay, that looks good. And we'll raise this up once again to 0.1. Okay, and I'm just going to change the shading mode to smooth shaded. Sorry, smooth wire shaded. And add another poly bevel just to give it a nice rounded kind of, packed sand look. Usually sand doesn't have, 90-degree angles here, so let's just bevel that a tiny bit, maybe 0.01. Okay. And again, we'll disable vertex splitting. Okay, and that looks all right to me. Might drop down a smooth node Actually, we can get rid of that. That's fine. Okay, and we'll make another null. And we'll just call this rainbow particles out. Enable that, and we'll hop back out. Okay, so we have the source for our grains, we have our collider. Now all we have to set up is the simulation. And since this is a beginner tutorial, you can set up Vellum yourself, but again, this is for beginners, so we'll just navigate to the shelf tools and use Vellum grains. Make sure you have, and we'll name this, sorry, rainbow particles. Okay, and with that selected, make sure you see these yellow line or the yellow outline. Just hit Vellum grains, and you'll get a few nodes that are created. One is called grains vellum, the other an auto.network. This is where the simulation is taking place, and you can tell we don't actually have any grains right now, so nothing has shown up once we've added this rainbow particles node as a source. And the reason for that is the particles are actually too large. So we're going to need to dive back into where we created this geometry. And by default, when we chose Vellum grains on the shelf, a few nodes are created. This is the one that you want to dive into. These are the grain constraints themselves. And so you can see by default, it's creating grains from a volume, which is our source geometry. And the default grain size is 0.1. This is not small enough in order to view. So the geometry is basically too small to pack these in. So we need to enable that. And we'll just change this to 0.01. So we'll drop by a factor of 10. Now you can see our grains are created. Okay, and we have quite a few of them, but they're stacked very regularly. So we can add a little bit of organic packing to that by jittering the scale, by enabling this. It'll take just a moment. Okay, I might pause this and then we'll come back. Okay, so a grain size of 0.02 seems to work pretty quickly for me. I think the jitter scale is a little strong though, so I'm just going to lower it to 0.75. Okay. And I think that's going to work better. I mean, we're still getting an organic result. Okay, that looks pretty good. Okay, so I'm going to keep it at this scale, but obviously you should, create particles at the grain size that you think kind of aesthetically looks good for you. I mean, this looks more like, I realize that the particle size is a little too large, but for the purposes of the tutorial, I'll probably leave as is unless I'm, pausing a lot and then resimulating. So we're just going to hit the middle mouse button and see how many particles we're actually working with. So we have 53,502 points. So again, the smaller you make this, the higher the number of points you're going to have. And it's entirely up to you how many you want to create. Just keep in mind the greater the number of points you have, the longer your simulation time is going to take. So let's dive back out here. And I'm going to turn off the Vellum grains node. I'm going to enable the .network. And we're just going to dive in here. and see what we're working with. So this is our source, our Vellum source, and you can see it's being activated on frame 1. It's only emitting once, so these particles are going to be engaged only once. So if you go continuous, every frame, the same number, so 53,502, whatever it was, is going to be simulated every single frame. Obviously, that's going to tank your simulation time. It's entirely up to you how much you want to emit from. I mean, if you have a grid that these points are being emitted from, and you're creating rain or something like that, then you're going to want continuous emission. But for what we're after, just only once is fine. Okay, this is the Vellum solver, and by default, when using Vellum grains, the substeps number is increased to 5. I would recommend going above that if you want a smooth simulation without a lot of jittering. I'm going to go ahead and put it to 7, but even a number of 10 or above is, it might be needed depending on your simulation. So we have our grain source, we have our collider, but we haven't set up the collider yet. So the collider needs to be set up separately, and you can do that inside the Autodot network, or you can just navigate back out here, select the collider, and name it a surface collider here in the Vellum shelf tools. Okay, so hop back into the Autodot network, and you'll see there's a little bit of a mess here. Hit L on the keyboard, and what's been created is a static object collider. So this is the path of the collider, which is referencing this geometry. A static solver, a merge node, and the rest of the information that we previously set up. So I'm going to go ahead and hit simulate, and we'll see what we're working with. Okay, so as you can see, the result is pretty pathetic. It's just going to basically fall and drop. Not much is going to happen, so let's just preview that. And but you can see that the particles are actually interacting with one another, which is kind of the hardest part. Okay, getting a little bit of play there. All right, so the next step would be to animate this collider so that we can get these bouncing around and interacting with each other in a more dynamic way. The easiest way to do that, and I've explained this in a previous tutorial, but I'll go ahead and explain it again, is to animate our collider geometry from the outside here. So instead of diving in and creating a transform node, it's actually a lot faster for the solver to calculate if we come in here and let's just create a simple expression using sine. So we'll just type sine. $f times, let's get a low frequency value, maybe 6. And we'll multiply that again by 15. Okay, and we'll see what we're working with here. So I'm going to turn off the simulation and just hit play. Okay, so we've got the collider rocking back and forth. If you want a few more degrees, you can add maybe 25. If you want it to be a bit more extreme, that might be okay. I'm just going to extend this timeline a bit, maybe 120. Okay, there we go. We get a nice smooth animation. All right, now You can add additional expressions if you like. One that I like to use often is just every frame, so $F plus maybe 8. So this is just rotating, I believe 8 degrees. I think it's degrees every frame. Maybe not. Maybe it's radians, but okay. And then we get a nice. Let's just make that 6. Maybe it'll repeat. It looks a bit smoother at 6. Let's try 4. I like 6 better. Okay. So the collider is rotating, and then it's kind of rocking back and forth, which is pretty much the same scenario that I had set up in the reference video. Okay. So I think that's all right. Now by default in the collider settings here, under static object, we have use deforming geometry ticked. So you want to make sure that that stays enabled, otherwise it won't take into account the animation that we just set up. Again, you can keyframe an animation if you prefer, and that's probably what you'll end up doing if you're making, this is just for simplicity's sake. I mean, you can easily manually enter in values and keyframe them using the timeline here, but since it's really fast and easy and you get a fluid motion, I'm just going to stick to using this expression and dive back into the auto.NET network. Okay, and I'll pause again and simulate, and we'll see what we're working with. Okay, so everything is simulated. We're ready to preview. Let's go. And the result is okay, but there's a few things that I like to change just to get more organic movement. One is it's almost as though we're creating a low resolution flip simulation. So this is kind of behaving a little bit like liquid, how it's pouring off the side. The particles aren't really clumping together. There's not enough friction, and I think overall the movement is it's a little too fast, and it doesn't really look high-end enough. So we're going to make some of those very basic changes. Most of them can be found in the Vellum solver here. I will need to simulate again, but that's not really much, it's not really a big deal. So I'll show you some of the parameter changes that will enable this to look a little bit better. Number 1, so we're just going to, I guess, navigate back to frame 1. And the first one is I'm going to change the timescale to 0.25. Actually, maybe 0.333. So we'll be operating now at 1/3 speed. And I think that'll just make, it'll make a lot of difference in terms of the quality of the simulation, and it'll give it a more editorial kind of look once simulated and once rendered out. Another thing that we want to do is to just increase the friction a little bit. So I'm going to dial up the dynamic scale here to 0.2. Okay. And if you want to add clumping with these particles, a really fast way to do it is to go into the Advanced tab in your solver and come down to Grain Collisions. And by default, the repulsion is at 10,000. We just want to lower this to maybe, let's say, how about 600? We'll try that. And everything else we can leave as defaulted. I think that'll be okay. And the default thickness of these particles should typically be the same as what we've determined the grain size should be. That way we don't get any kind of odd particle collisions. So we can actually link this number with the grain size, and that tends to work out great for the interparticle collision that'll be going on during the simulation, and I'll illustrate that in a minute. Okay, and the last thing I want to do is just above the merge node, I want to create a delete node. Okay. And yeah, I think a delete node. Oops. Sorry, a pop kill node. Now, we're going to, instead of creating a vex expression or rules for this, we're just going to go by bounding, and we're going to enable a bounding box. And what we want to do is kill a lot of the particles that are going to still be simulating down around here. So if you're not going to kill these, it'll still take into account that they're going to be colliding, dropping, and this is just an easier way to have, a little bit of, it's a time-saving maneuver. So we are going to take this, and by hitting the middle mouse button and just scrolling to the left, we're going to pull this down until it reaches maybe -2. And for size, we'll go maybe 8. Oops, a little bit too big, maybe 6 by 6. So let's just zoom out here. So this should cover, a wide enough area to kill all the particles that are going to drop out of sight once we set up our camera. So let's just set up a camera quickly. We'll bring this up so that we can see what's going on a little better during the simulation. Doesn't have to be perfect. Usually I just try to align the middle of the grid to this area just by eye, and then come in and change it after the fact. So we'll come down here, create a new camera, and then let's tie view to camera. So you can see this little lock pops up, and now we can navigate around, and it's actually moving our camera around. If you don't do that, what will happen is when you try to change the view, you're automatically popped up of your camera's view. So to come back in, you can see we haven't moved. So it's entirely up to you what you'd like to do, but for now I'm just going to tie this view. Okay. Now we'll hop back into the Autodot network. I think that looks good to go. So I'll go ahead and simulate, and we'll see what we're working with. Okay, so the simulation is done, and let's see what we have. Okay, I think I like that better. It seems that the movement's a bit more organic. I think the friction has helped. I'm just going to disable this and kind of navigate around here. Okay, so let's just stop this and see what's going on. Okay, so the collision seems to be working okay, and let's just tab out of this and go into the grain Vellum's node here. All right. Now I want to see the exact size that, or the exact thickness, I guess I should say, of these particles when they're under collision. So there's a handy node for that that's automatically created when using the Vellum shelf tools, and that is Vellum post-process. And you can just disregard the first tab and head over to visualize. And under thickness, if you enable that, you can see that the thickness of these corresponds to the grain size, so we're all good for particle collisions, or interparticle collisions, I should say. Okay, so let's just tab back here. All right, so let's middle mouse over this and see what kind of attributes were created. So we have velocity, we have target path, and we have position, obviously, mass. What we'll use to color these is velocity, and that's pretty handy. We can just hit tab, create a color node, enable that, and then we're going to use the attribute, the velocity attribute, sorry, with a ramp. By default, it goes black. And we're going to put the range from -2 to 2. Just see what's going on there. Okay, so it should be gray. And we'll just enter V for velocity. And automatically we get this kind of pretty sweet rainbow effect. Okay, that's looking pretty good. Now some last touches that you might want to add. We'll just navigate back to our camera. Are some randomizations of the particle sizes and the orientations. So one of the easiest ways to do that is to drop a randomize attribute node. And do we have a p-scale? Okay, well, we'll create a p-scale attribute as well. So we'll just go attribute create. Under name, I'll type p-scale, and it is a float, so we'll keep the class to point and the type to float. And we'll come here under p-scale, or sorry, under attribute name, type in p-scale. Let's enable that. Okay, now by default what happens is these get globally scaled. Now we need to change the scale to 0.01 to correspond to the scale of our vellum grains. And we'll just zoom in here and see what's going on. So you can see we're getting a range of values here from 0 to 1. And we're just going to go, uniform. And under min value and max value, we'll put 0.3 and 0.5. Oops. Let's bring that to 0.9. Okay, and now you're getting a nice randomized number here. Now the thickness, the inner particle thickness, is still at the 1 value. So if you need to kind of visualize that, you can keep this at let's say we'll go 1.1 and 0.9, 0.85 maybe. Okay, that's pretty subtle. I like how that's looking. another thing we want to do is create some custom geometry to be applied to each point. So we're going to lay down a copy to points node, plug this in, and before we plug in any additional geometry, we want to make sure that we pack and instance this. And this is going to save a lot of memory because currently we're working with 53,000 points, so we'll create a sphere. Make it a polygon. And let's just see what that's looking like. Okay, we'll come out. So this is what our sphere is looking like. Let's just dial the frequency back just a bit. And we will enable this. Okay, and the purpose I chose this geometry is to show you that there's something that's odd that's happening here, and that is the alignment or the orientation of all of these is somewhat uniform, which obviously would not happen in reality. So we're going to have to find a way to randomize the orientation of each one of these points, and that can be done relatively easily by coming back up here, adding another randomize, attribute randomize, and the default is color, so you can see how that's affecting everything, which is quite cool. You get these jelly beans. But the attribute that we want to use is orient. Now, by default, nothing is going to happen because orient is actually a go back here, uniform continuous. Orient is actually 4-dimensional. So we're gonna have to put 4 here, and you'll see we get randomization of the orientation here, which looks a lot more natural. And if you're increasing the grain size and therefore the simulation time, this is gonna help your renders a lot to catch, I mean, you can already see what's going on here. You're gonna catch kind of a randomized amount of reflections from your light source when rendering, which is going to give the appearance more of sand, or it's just going to break up the regularity of the geometry and give you a better result. So we'll come back. So I actually forgot a really important point during the simulation. What you in order to get clumping, you actually need to enable an attraction weight. So previously I just left this at 0 after changing the repulsion value to 600, but this is very touchy, so I've just added 0.0025 to the attraction weight, kept the attraction to 10, which was the default, and if I play through, you'll see we get just a lot better of a result. So you can see they're breaking apart and kind of flying off in chunks. You get some clumping as they fall down, and I just think it looks a lot more organic, and it'll help your animations a lot. Okay, so I'm going to again export to mplay, and we'll see kind of finalized result. Okay, so mplay has finished rendering the simulation intact with color, and let's just see what it's looking like. Okay, so it seems similar, at least to the result that that I was showing in the beginning of the video. So hopefully this this teaches you a little bit about vellum grains. I know there's a lot of tutorials that are floating around at the moment covering this topic, but I thought not a lot of them taught how to kind of contain the grains and how to get something a little bit higher end with the result. Most of them are just, dropping them onto the ground or what have you. So if you like this tutorial or you'd like me to cover something different in the future, just I guess let me know in the comments. I'm trying to make them better. For the time being, they're mostly going to be beginner tutorials, but check out my channel, I guess, for more and let me know what you think. So thanks very much, and you can get these free scene file as well as the Redshift file available for download on Gumroad and also at Patreon, which should be in the description. Okay, bye.